Hello, I'm Philip Meyer. Welcome to my video blog. In this video we will deal with a huge transformer. It's a three-phase transformer. I need to power my krypton argon laser. The laser doesn't work yet, so I need to get the transformer working first. Since I do not have any three-phase current in my lab, I have to work around with that with some tricks, and I think electricians should better not watch this video. All others should swear now that they won't try this at home. We are doing that here under controlled condition in a laboratory, and I know what I'm doing. I'm a professional, you are probably not, so don't try it yourself. And yeah, let's go down to the lab and see what's up with the transformer. So as you already might know from my previous video, is I have this offensive thing in my basement, and yeah, this monster likes to eat some current from this transformer here. And yeah, in this video I basically try to make this transformer running and try to get the correct voltages and yeah, maybe add some load, but of course I will not run the laser yet because there are many other things to do, and I think it's the best to just start with the transformer and see how to get that running. So this transformer runs from three-phase current, so will be connected to all three phases instead of one. So your normal household electrics, they run from one single phase, so you basically never get in contact with this three-phase technology. But at least in Europe, I know in the US it's sometimes different. Yeah, the networks are just different there and different wirings. But in Europe and especially in Germany, every household has this three-phase right into the house, so it's just there. And even if you don't have the wall plugs for that, you still have it. I mean, you could just add a wall plug by just getting the electrician into your house, and yeah, he would mount something like this. This is a Neo Z block into your fuse box and connect these three-phase power plugs there. But don't worry, you all still have three-phase electricity in your house, and yeah, so I do too. Even I'm not having the wall plugs, which is kind of a problem, but I think I can work around that. Yeah, since this is my first time I do something with three-phase electricity, I want to be a bit careful, so I want to measure the currents that are flowing. I'm interested in that. I have a Neo Z block, so if it comes hard on hard, this will protect me. And yeah, and this is some special additional thing here. So let's imagine only one of these fuses blowing, or yeah, somehow else the power of one phase gets interrupted, maybe by a circuit breaker in the fuse box. If that happens, one phase will be switched off, and that might cause problems. And I want to rule out any doubt about this. And so I got this from a friend, by the way. Thank you very much for donating this to this beautiful project. So this is basically a little measurement circuit that continuously monitors the three-phase. So if one of these phases is failing, it can it will switch. It has a little relay, and it will just switch off. And of course, you cannot hook up three phases for switching to this. So this has only one little relay inside. So I got this. This is a contactor. So this is basically a relay for very high currents, so a very powerful switch basically. So, and that will be connected to that, and then if one phase fails, it immediately would release the contacts and protect from whatever yeah, I just don't know what really happens to the laser, to the transformer when one phase fails. So that's just, yeah, better safe than sorry. And this is just a gigantic switch. So this is not a circuit breaker. It's just a switch. I already took it apart. It really has only the switch contacts inside. So yeah, the reason why I need this is obvious. I just want to be able to switch this thing off, and yeah, here you also see the 3 phases. And yeah, and I got this nice ampere meter from an online auction. So it goes up to over 20 amps. I intend to draw 16 amps at max. Yeah, I mean, that would just go in series into the circuit, and then that would be it, I guess. Yeah, so these are the materials, and yeah, I think I will just wire that up, and yeah, then we give it a shot and hope that nothing blows up. So I'm just thinking how to mount these, and this is one of these bars you need to, and you normally have near fuse box to hold all the contactors and switches and whatnot. Yeah, I think I will just get it somewhere here or here, and yeah, I think I'm gonna remove this plate and put it somewhere else, so I need the space for mounting all this stuff up, and I already have the holes here, so that will be easy to go into the case from all these assemblies here, go right into the case. So I think that's the optimal place to fix it here. So once again, a quick info what we are dealing here with. Yeah, just note the power rating here. So that is 17,000 volt ampere, which is roughly 70,000 watts. Yeah. The other things are not super interesting. I mean, if for the amps we have some maximum ratings, 45 amps, and the Schaltgruppe, which is basically roughly translates to switching group. So this Y here, so this Y just means that this thing has to be switched into star. So yeah, basically 2 modes, how you can wire up your 3-phase things and how they could be wired up inside. So that's more a thing with motors, but yeah, I mean, this is star, and you could also try to wire it up in triangle. I don't know if that works, but for a transformer you would never do that, so it's always star. So yeah, that's basically it. So let's move on. So here we have the inside again. So I think that wasn't super clear in the last video. Normally you have 4 wires, so you have your 3 phases, and then you have basically a neutral. And yeah, in this case, so this is the wire that comes from the outside, so that's where the power plug would go. And I don't know if you can see that really good, but these little wire piece here, so that's the neutral, so they cut it. And you might wonder how that works. So normally you have to have your neutral on your normal household electrics, of course. The current has to flow somewhere back to the source. So in 3-phase networks, there's a little magic behind. The thing is, the way the current flows back in this case. So first of all, this is a symmetric load. So you have your three loads, which are basically the 3 coils, and that's it. So that's symmetric, and these things are wired in star. So the currents which are flowing into here, they all come in a different angle, so they're all different. So it's not like you have 1, 2, 3 and they are all delivering all the same 50 Hertz. So that's not the case here. So the way that it works, these are picked up directly at the generator, of course, and the generator has coils, so it's basically an inverted motor. So you have your magnet that's rotating inside, and you have your coils outside. And so this magnet, while it rotates along the coils, and yeah, these coils are just mounted 120 degrees apart. So, and yeah, these phases have basically shift of 120 degrees, and yeah, when they flow in, and at the start point they even out. So that's why you don't need your neutral. Yeah, you should connect it. I mean, it's good, in general it's good taste to connect it, but you don't have to. And so that's what they did here. They didn't do, and I will do. I won't do either. So why doing it? I mean, it's a symmetric load, and yeah. So here we have the ampere meter connected up. So it's fairly simple to do. It just goes in series. So here we have the connection to the transformer, and here's the cable that goes to the power supply. Of course, there's other stuff to follow. All the safety switches, of course, they follow next. And yeah, I left the neutral hanging here in case I change my mind about the missing neutral. I mean, it would be good to connect it, because then I could use the transformer also for asymmetric loads, but I currently have no use for it. All my US stuff, the ALC60, the ASR33, and even the Superbrain, they all have their built-in step-down transformer, so I have no use here for yeah, having a US currents here. I just, yeah, I think I intend to use this transformer only with the laser, and that's a symmetric load. So yeah, okay, yeah, in case I need it, it's already there, and so that's fine. So yeah, I think I will mount that now, and then I move on with the safety switches, and yeah. So well, I finished some of the wiring work here. So these contactor switch, so that's now wired up. So that would switch the transformer on and off. So see these three phases coming out of there, they go straight into the ampere meter, and from there they go into the transformer. And yeah, these are the fuses and the switch, of course, and yeah, now we need to connect this thing to the device that continuously monitors if the three phases are still present. Yeah, and let's have a look at it. So here we have it. That's Dames UR 3005, and I looked it up on their webpage, and they are saying how to work, that this properly works is it needs to be connected to the L1, L2 and 3, and to the neutral as well. So we cannot get away entirely without neutral. We need it here in order to this thing to work properly. And they also tell it's depicted here, it's 0.85, so that's the minimum required voltage in order to make this work. Yeah, pretty simple. I think I will wire it up and see how this behaves, and learn a bit of it, learn a bit about it, because that's the first time I use one of these. So I got it wired up to this normal household cable, and yeah, of course I need to take care about the neutral this time, so I may have to make sure that this gets a phase and this gets a neutral. And yeah, I was beeping it through with the multimeter, and I noticed something I never noticed before. On the plugs, they marked the neutral. So this N on this side there, where it's not, but there's this N, and that means neutral. So they are kind enough to mark it for me. That's really nice. So, in finding out where the phase is, I use this device. It's a Phrasenprüfer from the Wow Holland Stiftung. Yeah, some people might not know the guy Warholland, one of the founders of the CCC in Germany. He used to have one of these always with him, and he called it the Phrasenprüfer. Yeah, it's basically a phrase checker. So it's not a face checker, it's a phrase checker. Yeah, was a funny, smart guy, this Warholland. I like him. He's dead already, but yeah, his spirit lives on. Okay, so enough jokes. So here we got the face, and yeah, plugs it in. So make sure that gets the neutral at the right side. So, oh, I hear it clicking. And here we have it. Here we go. So that's the L1. So the device just says L1 is okay. The others are not okay. Yeah, I wonder if this guy is smart enough to notice the 120-degree phase shift. I guess not. So if I connect the L1 figure to the L2 and to the L3 as well, I should get all these 3 LEDs lit. So let's try that out. So here we have it. I've wired all these 3 fake phases, and yeah, it's just thinking that all the 3 phases were present. So that's okay. That makes things a lot easier for me to check if my circuit works with even only using 1 phase. So that's fair enough. So let's integrate that into the circuit now. So I've all finished now, and yeah, let's see what we actually made here. So this is a circuit diagram of what I've actually made here, and yeah, this of course you all know, Back to the Future. No, just kidding. It's the transformer wired in star. So that's the star point where you could or could not connect your neutral. Yeah, this goes into the contactor switch. All 3 go into the contactor, and then they go into this Neo Z block, and then they go through the main switch to the power supply. And this little thing here is the monitor for the 3 phases, so it has connection to all 3 phases and to the neutral. I guess it only needs the neutral to detect if the phases are on, and yeah, for the power supply, of course. Yeah, it has a little relay inside that I've wired to L1 to have a power supply here. And whenever this thing thinks that the 3 phases are okay, it closes that little relay, and that goes into the the coil of the contactor switch. And yeah, then it needs to be connected to neutral, so to close the circuit from L1 to neutral. This needs 230 volts, of course, and then it closes the contactor switch, and the transformer runs. I want to give that a try now without the transformer connected to see if my detection circuit and the stuff works. And in the experiment I've shown you before, we know that we do not really need to connect it to the 3 phases. It's okay if we connect it to the, so to say, fake phases. We wire all them 3 together and put it to the phase, and that of course goes to neutral, and the thing should work. So this is it. I intentionally removed the contacts from the transformer, so the transformer is completely cut off now. I already have the 16 amps plug. I decided to go for 16 amps plug all the way through because yeah, there will be no 32 amps wall plugs here in that lab. That's just out of question. So yeah, and if I move to a different location, and if I'm lucky enough to have 32 amps plugs there, then I can exchange them. They are very cheap. Yeah, okay. I think now it's time for all the electricians and all you guys to turn off the video, because now I show you something that you might not like. Okay, this is it. And of course this is no more safe, sane and consensual, so this is already risk aware. Yeah, I've put a warning sign here, and I must advise you that you never ever try to build one of these, because that is really dangerous. I built it only for making experiments. Don't think that you can turn 3 wall plugs into 3-phase power. Yeah, technically you can, but it's very dangerous, and the reason for this is these, if you pull one of these plugs, normal household electrics, you can safely touch it here, but in this case not. If the other 2 or even 1 is still connected, that's still dangerous. And yeah, it's out of question that this is not okay. So don't try this at home. So okay, so now you are warned. So this is just basically a simple idea. I just look for 3 different power sockets with the 3 different phases present. I can measure that using the oscilloscope, it's no big deal. And then I basically turn them back into one of these. And for one plug I connected the neutral as I needed. So in the experiment we do now, I will all plug them into one socket, so I don't even get the 120 degrees phase shift, which I no need right now for testing my circuit. So this is for testing only, okay? So don't do that at home. Yeah, this looks pretty disturbing. Yeah, I've plugged them all into one socket. I mean, that would of course never ever work on a real 3-phase load. Don't forget that. So once again, don't try it yourself. So I've plugged it in now, and yeah, let's see if this thing actually does something. So notice a big bang, so that's from the contactor switch. So now 3 phases are contacted, and you see all 3 phases are present. So the contactor is switched on. The transformers, of course, they cut off. And now let's simulate a fault. So let's say, for example, this S3 goes faulty for some reason. So, and it immediately switched off. These 2 are staying lit because the L1 and the L2 are still intact. So they're fine. And yeah, let's turn it back on. And yeah, so its power is restored now. And now let's say L1 goes faulty. So, and now all 3 are off. That's just because L1 is also supplying this circuit. But the effect is the same. The contactor is switching off. So the hum, by the way, is from the coil inside the contactor. These contactors are really powerful relays. They are not, yeah, they're basically not a relay, so that's why they are called contactors there. It's a bit humming. And then I turn the phase off here. You see the coil moves forward and to disable the contacts. And that's a really powerful switch. It's used to switch high currents normally, so we can see that here maybe. So that's a 63 amp one. So yeah, there you need powerful switches. So that's what it does, switching currents. So next thing I wanna check is if these 3 phases here are switched properly. The way I do is I just pick my multimeter and tap all 3 So this is 230 volts, fine. 231, fine. 231, so they're all three fine. So now, again, let's simulate a fault. So it's off now. Let's see if they still have something on them. No, nothing there. Nothing there. So they're all fine. So switching works properly. And yeah. And the measurement circuit here, it even displays that correctly. L3 is faulty, it says. Yeah, so this kind of works, and yeah. And I think the next we will do is we just wire that up to a real three-phase source and check out the transformer. So it's been a while. I decided to give the transformer a nice painting, so I have it coated it now in a nice gray color. And I decided to use these upper hole here to bring in the power. So it's plug here. It's now connected to this, so it's a lot nicer and safer as well. And I cut a hole behind this meter. I cut a hole to lead all the wires through, so there are no wires coming out visibly coming out other than these two. And I got nice stickers. Engineers love warning signs and warning stickers, so that's a must. And yeah, you have place now. So that's now a really nice appliance with new wheels as well. So that's really beautiful. And I think we give it a shot now. Okay, now we will do again some kinky stuff. So electricians, please look away if you cannot stand this. These are 3 extension cords and 3 little wall plug power supplies, and I hooked that up to the oscilloscope. And the magic here is that these 3 guys here, they are all wired up to a different phase of the house. So, and that's what we see here. Here we see all the 3 phases, and they all have a shift of 120 degrees. So that's basically a perfect 3-phase current source. Okay, besides the fact that we are not using proper connectors, but from the physics perspective, it's not much different as a normal, usual 3-phase power source. So the only thing is that the wiring is a little dangerous, but we are doing that here under controlled conditions in a lab. Don't do that at home. You are warned. This can be dangerous. Again, we now use our magic cable, and it doesn't matter which one goes into which. For motors it would matter, because that would define the direction the motor rotates. And what I will just do now is find out where the phase is. I do it with the phase checker. And yeah, then I will wire them up. So it's now connected, and we should have 3 phases in this wall plug here. So that's the way you count it. You count it at the beginning of the earth hole here, as the earth connector is, and then you have 1 phase, second one, and the third one. And this one, of course, that's our neutral. So it's all wired up now, and we are ready to go to connect the power. Wow, yeah, now we are sitting in the dark. So well, that's something you should all be familiar with, that it's our fuse box for the basement and for the first level. Yeah, it has blown to circuit breakers. The third is still intact, of course, because when it has blown two, there's no connection anymore. So yeah, you most likely just blow two at once. So now they are back in, so power is restored. And I think now we have to rethink the whole thing and think about what went wrong. So why is this thing blowing the circuit breaker? If you have worked with transformers before, you maybe have seen the data sheets or somewhere else a graph that looks like this. So, and yeah, for H here, let's see, field strength, then we have the flux density. So that's an hysteresis loop, and it basically shows what happens inside the transformer core. So when a magnetic field is applied on the outside, that's on that axis here, then it shows what's the field strength, the flux density inside the core. And so when we have the current flow, it's a sine wave 50 Hertz, when it starts up the very first time, so the transformer is completely new, just unpacked and connected to the power supply, then it gets magnetized. And then let's say it's a turning point, magnetic field is changing its polarity, then it moves this way down, then it changes polarity again, we are here, it moves up again, and that's the normal operation, goes back and forth all the time. So the core gets magnetized in the one direction, then in the other again, and so on and so forth. At this point here, when we increase the current through the transformer coil, we also increase, in the very beginning, we of course increase the field, the flux density inside the core as well. But there's a point where we can increase the field strength as high as we want, but we do not get much more out of it. It slowly goes up linear, but it doesn't do much. This is basically a cut-off situation. So we call this point the saturation of the core. So the core is saturated; it cannot take any more magnetization, so to say. And the problem with this here is when the core is saturated, there's a lot of stuff going on, the Lorentz force and a lot of quantum mechanic stuff I cannot explain here right now. But the situation is that the core is behaving like it wasn't there. So there's no more limitation of the current inside the coil around the core. So the only thing that limits the current inside the coil around the core is the ohmic resistance of the wires, and that basically means short circuits. So we must avoid that we reach this point here. So we only are basically allowed to move in between, go very close to the saturation and then go back. We may not exceed this point. So that's basically our constraint here. But obviously we blow the circuit breaker, so that must mean that we've gone out of this valid range. So we overdone it. So, and the reason why that happened is is just because the core has some memory capability. It has a remanence. That's also the reason why this curve is coming up, because it's getting magnetized, and then the opposite magnetic field from the outside has to turn all the elementar magnets, has to turn all of them again, because they are in a certain positioned by the positive magnetic field, and then there's a negative magnetic field working against, and then we have to work against these pre-magnetization. That's why it's taking in a different way down. And if you switch the transformer off, it will keep a certain magnetic flux, so it will drop a bit, of course. And in air gap transformers, for example, it drops almost down to the basically to the point where it's not magnetized at all. But in our case, we have a very tight pack transformer without any air gaps, so we want to avoid that in our setup. So if you switch off, for example, at this position, you will always have some we will have a BR, so that's the remainder of the flux density. So in this case the H is 0 then, because its coil is switched off, and then we end up with the remanence, the BR, and that's basically a stored magnetic field inside the core. And when we start again, we will not start off at the 0 here, we will start off here, and then we will immediately hit this point and go even farther. So there will be a very high current inside the coil, because we are immediately going into the saturation. So the reason why the circuit breaker is blown is just because we are hitting and going below the saturation point. So basically our core is saturated, and that basically creates a short circuit. And in a real world setup, when you normally protect transformers like this with a very higher rated circuit breaker, like let's say 32 amps, then it most probably won't blow the circuit breaker. But in my lab I only can draw 10 amps, and that immediately blows it, even with no load attached. And there can also be the opposite way. I mean, if you switch on at the right position again, you can be lucky and you can start somewhere here. So let's say you switch on here, then you have enough distance, so to say, and you won't exceed this very far. The current peak would be less, but if you switch it on here and you are here, then it blows it. So, and in real life, if you switch it on at the wrong position with properly rated circuit breakers, it will hit his head over and over again, and the curve will settle down to the middle position slowly, and then then things would be fine again. But okay, in my lab with 10 amps only, I cannot afford it. I certainly need a current limiting device that basically puts an additional resistance in between the circuit in the very first milliseconds when the device is powered up, and slowly tapers off that resistance then. So that would basically avoid the current peak in the beginning and start it up softly. There's just no other way. And what's basically the source of this problem? I mean, the root cause is just everybody wants small transformers. I mean, I'm happy that this transformer is not even bigger than it already is. And the way these things are designed, they are just designed that basically they save as much metal as they can, and so they have a core that where the hysteresis exactly fits in and there's no spare space or something, no reserve, so it just fits in. And yeah, if you are somewhere pre-magnetized, you will hit your head at these walls, so to say. Yeah, so that's basically weight and material. That's of course a design constraint. So yeah, so that's it. I think I would say I already ordered a current limiter device, and I think we go down to the lab and try it out if that really helps us. So since we now understand that the switch on current is the problem, we need to find a mitigation, and the mitigation is called a current limiter. And this limiter device that works by limiting the current during the switch on phase. So for the first milliseconds, it adds an additional resistance in series, resistor in series, and slowly switches it off, so it tapers off. It's made with these thermo resistors, and here you can see the description I got with it. So that's how it works. It limits the current at the beginning below the switch off current of the circuit breaker, and then the resistance of the thing slowly tapers off and releases basically the full current to the device, and by this it limits the initial switch on current, because once the transformer is running properly, it only draws a very tiny amount of current if there's no load attached at the output, of course. But yeah, in the beginning the current flow is high, and we need to limit that. So I've opened the device now. Basically I'm violating the warranty in order to show you how the thing works. So here we have these three thermistors, but they are basically reverse thermistors. They have a negative temperature coefficient, so the hotter they become, the lower the resistance. So that's how it works, and they're made out of kind of a ceramic material and have some sensor-like thing on the back. So these there is definitely a lot of watts there going through there, but it's only for a short time. So as soon the startup phase is done, there are relays that are shortening these out, so they are only in the circuit at the very beginning, and that's how we get the behavior we need. A little current limiting at the beginning, and the limit that is put on the current should taper off slowly, like depicted here. So that's how they technically implement it. There's really not much in it. A few relays. It's just a few parts in there. Nothing special. No microcontroller. No. Yeah, it's just plain old circuit design. So let's now close the cover again and try this thing out. So now the current limiter is in the circuit, and we can try again. And that's it. Peaceful humming. So let's now take out the multimeter and check the voltages if they are correct. So let's check out the primary side first. Here we get a 220. That's a 233. And there's a 220 again. And yeah, the US side, basically the secondary. Here we have 115 roughly. Yeah. And here we have that's 126, and Here we have 116. Yeah, I think that's fine. So I can also check the star point here. There we get 6 to 7 or 6 volts. So that basically means that the star of this transformer is a very little bit off center, but I think that's still within the in the valid range. So that's it now for now, folks. I finished getting the transformer running, so it really seems to run very well. And yeah, unfortunately for this year it will be it, so there will be no more tinkering with the laser this year, so that will be left for next year. And yeah, it's still completely in the dark if this thing even works. So yeah, at least we got a nice transformer. I think that's something. So yeah, and anyway, I mean, in case this laser doesn't work, I think I will get another gas laser. I mean, now this is a so interesting topic. I mean, I think I barely can leave my fingers off. So yeah, anyway, this thing will be useful in the future anyway, so that's also why I restored it. And yeah, I think I just wish you a nice Christmas and a Happy New Year. So take care and goodbye. See you soon.